Okay, we're at the hour, so I think let's start with the first session of PAM 2021. I have the honor to share this session. My name is Mia Kühlement. I'm working at Ericsson Research in Aachen, Germany. I was part of the TPC this year and had the joy to read a lot of nice papers. And I'm also very excited about the next 3 talks we will see. So this session is about impacts we see from COVID-19, different measurements from different angles, what happened. The first talk will be looking into Zoom, which has, as we all know, seen a huge traffic increase. So that's very interesting to see what happens there a little bit, or to kind of debug measure what happened there behind the scenes. The second talk will be about what happens on the provider side. Another very interesting insight. And the third talk will look a little bit into changes in DNS. So for the measurement community, this has been exciting times. I think we learned a lot. So I have to say before we start that this session will be recorded. So if you participate in the session by asking a question or unmuting later on, we assume that you consent to be recorded and be eventually on YouTube. And the talks are all pre-recorded. The talks take roughly about 8 minutes, and then we have another 7 minutes for questions and answers. So we have hopefully a lot of interactive time. I would like to ask you to put your questions, or at least an indication that you would like to ask a question, into the Slack channel. We have an own Slack channel for the session, which is PAM 2021 Session 1 COVID-19. And I will have a look at the Slack channel, try to call you up, and then you can unmute yourself and ask a question yourself. So hopefully this will be a little bit more interactive then. If you don't want to unmute but still ask a question, please indicate this in Slack as well. Then I can try to read your question. Or you can also just, of course, ask questions in Slack without having this interaction here, because given the talks are recorded, the speakers can actually answer questions already during the talk, or you can also talk to them later, of course, if you have further questions after the session. Okay, with that, I think we start with our very first talk. And the first talk is from Konstantin Sander. He is a second-year PhD student at the RWTH Aachen University, at the Chair of Communications and Distributed Systems. He's working on measurements, protocol performance, and also machine-based learning optimizations. And his talk will be, as I already announced, will be about having a closer look on Zoom. I really enjoyed the paper. I happen to be the chairperson for the paper, and I can say that they put a lot of additional work into this paper, and I think it's a really nice paper now, so I'm looking forward to the talk. Let's start the video.
Hi, my name is Konstantin, and I'm going to present you our paper in which we take a first look at Zoom's congestion control and how it's behaving when competing for bandwidth. We specifically focus on Zoom as it's using UDP to transmit its video, so it has to implement its own congestion control, and not TCP, whose congestion control behavior is a frequent focus of research. Moreover, Zoom has recently seen an increase in usage during the COVID-19 pandemic due to the increase in remote working. Hence, we can see an increase of traffic being governed by an unknown congestion control with unknown effects onto internet stability and internet resource sharing. Hence, we analyze it. In the following, we will show you the most interesting findings which fit into 8 minutes. Please have a look into our paper for further information and more details. We observe Zoom's congestion control in a semi-controlled testbed, where you have a bottleneck in the middle, whereas in the Zoom client and the TCP client have to compete for bandwidth. We then analyze the flow rate equality, the queuing delay, and the packet loss, to then see how Zoom is behaving. Moreover, we also analyzed the effects of deploying an AQM on the bottleneck, on the resource sharing, and also on the perceived quality of Zoom via a small-scale user study. However, before getting to the user study, let us have a quick look at Zoom's general behavior. Here we can see Zoom's sending rate at a 50 milliseconds round-trip time, 10 times BDP queue size, 4 megabit per second bandwidth bottleneck. After around 100 seconds, we reduce the bottleneck bandwidth to 0.5 megabit per second. We can see that Zoom does not directly react, but takes around 20 seconds to then also reduce its rate to less than 0.5 megabit per second. However, on the downlink, in contrast to the uplink, shortly after reducing its rate, Zoom increases its rate again. And this time we can see packet loss and also increased queuing delays. This leaves the question open how Zoom is actually behaving when there is a competing flow. Hence, we now add a cubic flow and look at the flow rate equality values. Flow rate equality is a metric from one of our previous papers, and it maps the bandwidth usage between TCP and Zoom in our case. For example, -1 means that TCP dominates, so uses all of the bandwidth, while 1 means that Zoom dominates. Everything in between maps to the fraction of bandwidth usage between TCP and Zoom. For example, 0 means flow rate equality, so both Zoom and TCP use the same amount of bandwidth. We can see for bottleneck bandwidths of 0.5 to 2 megabit per second that we achieve flow rate equality values above 0.5. So Zoom uses more than twice the amount of bandwidth TCP gets to use. So we can say Zoom dominates in this low bandwidth scenario. We would like to note that this is not necessarily bad, as flow rate equality is a bad fairness metric, and Zoom's goal is to simply keep the video going, which is sensible. However, for example, for 4.0 megabit per second, we can see that we also achieve flow rate equalities much closer to 0 and below. So in this case, Zoom yields more bandwidth to cubic. For BBR, we can see the same behavior, but it's more pronounced, so BBR gets bigger shares more early. When increasing now the queue size to, for example, 10 times the BDP to have an overlarge queue, we can see that Zoom's behavior changes drastically. In this scenario, we can see that Zoom does not really yield anymore, but uses around twice the amount of bandwidth that TCP gets to use. However, until now, you only looked at the downlink. Hence, we also now show you the uplink, which is denoted in blue here. And we can see that the flow rate equality values for the uplink are lower, so TCP gets more bandwidth. So we can say Zoom is less aggressive on the uplink, and we would even say that the client congestion control on the uplink and the backend congestion control on the downlink differ. Maybe they are even adapted to the bandwidth asymmetry on residential access networks, where the uplink bandwidth is typically lower than the downlink bandwidth. We can see, for example, for 4.0 megabit per second at an overlarge queue, where previously Zoom did not really yield any bandwidth, that now cubic can reach flow rate equality values of 0 and sometimes even a little less. The same holds for BBR. However, throughout all scenarios, we can still see fluctuations and high queuing delay. For the high queuing delay, we, for example, deployed the AQM CODL. CODL could indeed reduce the queuing delay, but was not able to improve the flow rate equality. Hence, we go one step further and deploy FQ-CODL to see whether it can improve the flow rate equality. FQ-CODL is the flow queuing variant of CODL, where every flow, so the Zoom flow and the TCP flow, get their own queue, which is then handled by CODL. The queues are then also handled in a round-robin manner. Here we show you the tail drop queue of 2 times BDP as queue size in red, and the FQ-CODL queue results for the flow rate equality in blue. And we can see that with FQ-CODL, the flow rate equality improved. We are near equality on the downlink, so we can reach results very close to 0. On the uplink, the results look different again. Here, Zoom yields earlier. For example, cubic already achieves now flow rate equality at 2.0 megabit per second. However, Zoom does not only yield more bandwidth, but also benefits from the improved fairness. For example, for BBR at 4.0 megabit per second, we can now see that the flow rate equality improved for values below minus 0.5, so where BBR gets a high share, up to values much closer to 0. So Zoom now also gets a bigger share. However, looking at this and the massive differences, and the general observation we had before that Zoom does not directly react on packet loss, the question is whether FQ-CODL is actually making Zoom react, or whether FQ-CODL is just dropping Zoom's packets. Hence, we next look at the amount of received and dropped packets. Here we can see the received and dropped packets for Zoom and TCP at a tail drop queue and an FQ-CODL queue. We can see that for TCP cubic, the amount of dropped packet increases by around 33%, but we can also see that the amount of received packets increases. This is for one part due to the improved flow rate equality, because TCP cubic now gets a bigger share, but also due to the retransmission. For Zoom, we can see that the amount of received packets does not really change. However, the amount of dropped packets increases by around 200%. So Zoom does not react, does not change its sending rate, but FQ-CODL is increasingly dropping its packets. The question for this is whether this has an influence on the quality of experience of Zoom. Hence, we also conducted a user study where we asked 10 of our colleagues to rate the video quality, the audio quality, and the interactivity of a Zoom conference on our testbed with the same network settings as before. We then added an FQ-CODL queue and a tail drop queue, and a cubic flow, which is competing with Zoom. You can see the results here, and we can see that for most of the results where there is competition between Zoom and a cubic flow, that the confidence intervals overlap. So the results for the competition are insignificant. However, when looking at this, we can see a trend against FQ-caudal. So there might be the change that using FQ-caudal is even detrimental to the quality of experience of Zoom due to the massive packet loss, although there are the positive effects of using caudal and decreasing the queuing delays. So in all, we can see that Zoom implements a congestion control with an at least to us unknown behavior, and it does not rely on a traditional TCP congestion control algorithm, which is known to us. Zoom's congestion control tends to claim high shares of bandwidth on low bandwidth links, specifically on the downlink and with over large queues. However, we would like to note that this is not necessarily bad to keep the video conference usable, as flow rate equality is no good fairness metric. We also saw that applying FQ-caudal to the queues improves the flow rate equality. However, Zoom does not really react, but FQ-caudal is increasingly dropping the packets of Zoom. We then also looked at the QoE effect of this packet dropping, but could not find statistically significant results. However, we could see a slight trend against FQ-caudal. So there might be the chance that using FQ-caudal decreases the quality of experience of Zoom. So hence, although research recommends the deployment of FQ-caudal, in our case, it could decrease the quality of experience. For future work, we imagine looking at Zoom's congestion control in the realm of explicit congestion signals, and also when Zoom flows compete with each other. Moreover, we would like to enlarge our user study to improve it. Thank you.
Yeah, so Konstantin, thanks for the talk. If you want, you can also turn on your videos and people can see you live now.
I already switched it on.
Okay, so then it's just me who has a weird setup and can't see it. Okay, perfect. Now I can see it. So thank you. Let me ask the first question. I believe you did like some, after the paper was finished, you did some additional measurements, or maybe you're still doing it, I don't know, hopefully. So did you see any trends, any changes over time?
No, so we actually were kind of cautious about this because our measurements were quite long, and we was, I don't want to say scared, but a little bit cautious about maybe that Zoom is changing its behavior, and all the data points you can see in our paper are sorted by time, and we didn't see anything that has been obvious that there has been a change in the behavior of Zoom. So no. At least not.
So, but remind me, when did you start your measurement?
We started back in July, and it took about to October. That has been me again.
Okay. Yeah, so would be interesting. So I could imagine that on the long term, they do adjustments, and maybe they also did something like right when the pandemic started. So definitely something to still look at and see what's happening.
Yeah, we've been using the same Zoom version throughout all our experiments. Maybe there's also a change when you update your Zoom version. Maybe then there's some handshake or something like that.
So we have a question on Slack now. Roman, do you want to unmute yourself? Or I can read it. So he said, thanks for the talk. And you several times mentioned that your metric is not perfect for fairness. So which other metric would you use, and why did you not use it then?
Yes, we specifically used flow rate fairness because that's actually what flow queuing caudal would improve, or weighted for queuing in general would like to improve. So we specifically looked at that. And as we could see, the flow queuing caudal could indeed improve the flow rate equality, but the question is whether that is actually of any good for Zoom or the TCP stream. There are, of course, other metrics. You could use something like PAM, but when you then look at throughput time, you get back to the same point I already mentioned in the video, that at some point, Zoom is a completely different type of class of application. And the question is whether it makes sense to have then flow rate fairness, but Zoom cannot be used anymore, or whether it's okay that a TCP stream gets a little bit less bandwidth, but Zoom can continue to be functional.
Yeah, I can add a point, because we had because I was a shepherd, we had some discussion about that as well, I guess.
No, sure.
Somebody unmuted and talking in the background, not sure. Okay, now it's gone. So I can add maybe one more point is also I'm active in the IETF, and there was a lot of discussion recently about what TCP friendliness means, and kind of they came up with a definition that you should kind of not starve other traffic, right? That's the important part. But trying to have equal flow rates doesn't always make sense, as you say. For this application, there's a point where it just doesn't work anymore. So that's, I think, a longer discussion to have for this research community. Let's see, are there any more questions on Slack? We have still some time, I think.
They have a lot of data available, then they set the quality level really high, and then takes the clock.
Rinomine, toglielo quello.
No, but it sounds,
We
it
have
sounds
some-
great. Cool.
Be unmuted,
So-
you shouldn't be unmuted.
Any question?
Okay.
I then I will change the bottleneck, which just here.
Then maybe do a link utilization graph.
Okay, yes.
Okay, cool. Good job.
Can you just
So next week is vacation.
Yeah.
So yes, I guess see you in 2 weeks. Or a part
Say
of
2 weeks.
but you should note it that it seems like everybody's right. Everything you said.
I have no idea. I didn't understand anything, to be honest.
Yeah, I think this is just a technical problem that everybody's unmuted, and I don't like everybody needs to mute again, or Sebastian, our host, needs to mute everybody again. That just doesn't work this way. Okay. Now this seems to be fixed. So sorry for that. Let's see if we have some more questions. Okay, in that sense, I think we are waiting for more results from you in future. Thank you very much for your talk. I hope people ask more questions on Slack for you or contact you otherwise, and we just move on with the next talk.
Thank you.
And our next talk will be given by Shinan Lui. He's a second-year PhD student as well from the university in Chicago, working with Nick Feemster there at the computer science department. His interests are in network systems and also security and privacy. And in this paper, he did look into what happened basically behind the scenes. What did the providers do to cope with this increased traffic demand? So very excited to see this talk. Let's start the video.
Welcome to our talk today. I'm excited to share our project categorizing service provider response to the COVID-19 pandemic in the United States. I am the presenter, Shinan Liu. Me and my advisor, Professor Nick Feemster, we come from University of Chicago. And this is a joint work with Dr. Paul Schmidt from Princeton University and Dr. Francesco Bonzino from University Savoy Mont Blanc. The COVID-19 pandemic has significantly impacted our daily behaviors, no matter it's in work, study, or other activities. As these activities become online only, when facing this new trend, the broadband internet has stressed because of these extra traffic loads. Previous study has shown that resulting changes are observed in Europe. For the overall traffic volumes, it increased 15 to 20%. And in Italy, it resulted in round-trip latency of about 30% higher than normal. Some announcements are also made by other entities to respond to such traffic shifts. Service providers, regulatory agencies, they claim that they implemented various responses to those shifts. For example, the Federal Communication Commission announced an initiative to grant providers additional spectrum. However, the validation of those effects in the US, and the actual measurements are still missing. So in this paper, we explore the traffic effects in the United States from a longitudinal perspective and measure the actual service provider responses. We seek to answer 3 questions. First, we want to understand in the United States how the traffic patterns change as a result of COVID-19. Second, considering the stress from the traffic shifts, what were the results affecting the performance? Third, if the performance faced gradations, how did service providers respond? In order to answer these questions, we cover multiple data sets to conduct different analysis to reveal the changes in the traffic demand and interconnect capacity. We used Internet Connection Measurement Project. Basically, the project covers 7 anonymized access ISPs and about 50% of the broadband subscribers in the US. To understand performance, we explored the ongoing FCC Marine Broadband America project. And also to understand some of the service providers, such as video conferencing apps, we used the IP prefix advertisements. We start with the first question: how did traffic demand change? We answer it by inspecting the link utilization. Here we show 2 plots of 99th percentile utilization. On the first plot, ISP A witnessed a dramatic change around March 2020, which aligns with the beginning date of lockdowns. The ISP B does not show that significant change, so we normalize it to the maximum capacity of each link. So on the second figure, both of them show significant changes. This contributes to 30% to 60% of increases in the traffic demands. We also investigate how traffic patterns change between ISP A and each of the peers in both upstream and downstream. We picked 1 day before and 1 day after lockdowns. In general, we see that the traffic patterns to peers do not vary greatly between the 2 dates. But we do see that the traffic patterns to some peers change significantly. For example, some peers show an increase of upstream utilization by 2 or 3 orders of magnitude. Now we come to our second question: what was the effect on performance? We show the daily changes of latency, average round-trip time, over the course of 2020. It shows a 7-day moving average of it. We observe an increase around lockdown in this latency by as much as 10%. This increase in mean latency is significant because it corresponds to 30x standard deviation among all white boxes. On the per ISP level, we show the 99th percentile. They did show some deviations from normal levels during lockdown for certain ISPs. But notably, in many cases, the same ISPs experience deviation in latency during other periods of time, like December holidays. Now I'll come to our third question: how did service providers respond? We calculate the total interconnect capacity for 2 anonymized ISPs. To show aggregate infrastructure changes over time, we take all of the data points in each quarter and perform a least square linear regression. The overall trend shows how these 2 ISPs in the United States aggressively added capacity at interconnects. For example, the first quarter of 2020 is twice as much as the first quarter of 2019. On the advertised IPv4 space, we also witnessed a huge surge in the space number. It is like 2x to 3x increase in those advertised apps After we answer those 3 questions, here are the takeaways. We observed a 30 to 60% increase in peak traffic rates for 2 major ISPs in the US. Correspondingly, we witnessed significant increases in latency in early weeks of lockdowns, followed by a return to pre-lockdown levels. Meanwhile, we found aggressive capacity augmentation and ISP interconnects and the addition of IPv4 address space from video conferencing providers. We are the first known study of interconnect utilization and service provider responses to changes in patterns resulting from COVID-19 pandemic. This study still offers a somewhat limited viewpoint to these effects and characteristics, and we truly encourage the community to explore more around it. Thank you for your time.
Okay, thanks a lot for your talk. I see you're also on video already, perfect. A really interesting paper, a lot of measurements, really good to kind of understand what happens a little bit behind the scenes, because I think what we all just see is that the internet just worked during this high increase in traffic. Like why it worked, we might need a little bit of understanding, a little bit research still. And we do have a question on Slack. Jan, do you want to try to unmute? Let's see if that works now. He can't. So Sebastian, can you try to unmute Jan?
I was, yes. Can you
Okay.
hear me?
Yes, we can. Perfect.
Oh, all right. Then hi everyone, and thanks for the nice talk. I was wondering whether or not the increased latency that you saw is mainly due to more queuing or congestion, or does it have to do something with the behavior, how people use the internet? For example, if you work at home, you typically have to contact all your corporate infrastructures, which might not be as well connected as, let's say, the big internet players' infrastructure that we typically use all day.
Yeah, thanks for your question, and that's a great question. Actually, those RTTs are measured by the FTC project, and we don't know like the root cause of it. But my best guess is like, yeah, there must be some kind of like reasons. Like there are many users that are working from home and they are connecting to services that will cause more traffic, and thus results in more latency there. And yeah, and I think that might be because of the infrastructure limited capacity. Yeah. Okay.
Okay, thanks.
Yeah, we have a follow-on question from Oliver Gasses, so maybe we can unmute him as well. You want to ask this yourself?
Yes. So thanks for the talk. I have a question, and it goes into the direction of whether you saw any difference in latency depending on the location of the clients. So whether they were located in metropolitan areas or rural areas, for example.
Yeah, thank you. So actually, we haven't had the chance to look into like the area differences, but we computed these latencies from like the 10 major cities from the US. So I think our results mainly like reveals the patterns in more like metropolitan areas. Yeah.
Okay, thank you.
Thanks. And we have another question from Midi. Let's see if you want to ask it yourself. Not sure if you're able to unmute or if we can unmute you. Try again. I thought we heard something. Then let me ask the question. Okay, the question is, are ISPs any different in terms of users and organization? If so, was there any difference visible in the results based on these differences?
Yeah, thanks for the question. I'm not sure if you are asking like whether it's because we have different populations or it's more based on the ISPs. So at least for the interconnected set, I think it's more about ISPs, and also the FCC data set also provides us like the ISP level some metrics, but you may think they are not like representative for the whole population, but actually the FCC project, like the MBA, is a project that they made for policy making. So I think that's also like worth looking into.
So maybe the question was, did you look at different ISPs? Are there small and big ISPs, or ISPs that whatever only serve certain areas and so on? And could you see a different traffic pattern, different network patterns there?
Yeah, sure. If you go to our like slide 7 or something like that, you can see that definitely different ISPs, they have different different patterns. But one thing that in common is like they like are still missing. Yeah, thanks. So can you also go like a little bit to I will have some thoughts for different ISPs. Especially on the performance. Yeah, maybe I can just say it. I think one thing in common is like some ISPs, they don't respond to they don't we didn't observe any drift around lockdown, but we actually, for some other ISPs, we observed the drift for lockdown as well as some like the Christmas period. So I think those kind of drifts are not like COVID dependent, or it's more like the we can also observe something like as a seasonality factor. So yeah, that answer your question.
So did you reach out to some of the ISPs and figure out what they actually did, if they did some specific measures during this period?
Actually, no.
Okay. And we have one more question from Kingsley. Can we try to unmute you maybe? And see if you can ask your question yourself. Sebastian, can you unmute? Now we might hear something. Yes, try again. Maybe not. So I asked the question again.
Yeah.
He said they have some knowledge about the traffic volumes in the past, for example, around the World Cups. So they have an idea what to expect. Is there anything you realized that you think was dramatically different from these kind of events?
Yeah, sure. I think that's a great question. Actually, this is something we also observed in the past, and in terms of like the traffic changes, it's very similar, but one major difference is that the COVID is last a bit longer, and it's lasting like for a year now, and that like results in a longer response from the the ISPs and also other organizations. And for World Cups, it's like a relatively short time, and the response a bit quicker because that's more they have some provisions on those kind of like scheduled events. But for this kind of unscheduled event like the COVID, it is harder for them to respond in a longer period.
Yeah, totally makes sense. So well, let's see what will happen next. Thank you very much for the talk.
Thanks.
And we probably move on to the next talk. That's already the last talk for this session, and it will be held by Roya Kawaoka. He's an undergrad student at the Network Security Lab at the Waseda University in Tokyo, where he's also working on projects related to network security. We're excited to have you here for the talk, and we will start with the video.
I'm Ryoka from Waseda University. Thank you for attending my talk. Today, I will talk about COVID-19 related domain names. This is joint research with the Secure Platform Laboratory at NTT. So, let's begin. COVID-19 has impacted the world greatly, and related domain name registration have been increasing accordingly. As more and more people spend their time online, there are more users interacting with domain names in general. Under these circumstances, it is very important to understand the origin and usage of domain names related to COVID-19. To this end, we have conducted a survey on newly registered domain names related to COVID-19 called COVID-19 DOMs for short, to analyze the impact of COVID-19 on people from the perspective of domain name registration and to clarify the actual registration status and usage of COVID-19 DOMs. We conducted 3 investigations on approximately 165,000 new domain names registered between the end of December 2019 and the end of September 2020. We first found the peak of domain name registration was 1 month ahead of the pandemic. Secondly, we also found about 70% of the domain names were actually related to COVID-19. Finally, we found that about 3.5% of the domain names were detected to be malicious. Given the reality of the situation, issue must be addressed with caution. From here, I will explain how we collected our data. Then, I will show the analysis procedure and the results. So, let's move to the data collection method. I will show the method of domain name collection and website collection. As for we collected domain names, first, from a large domain name database, we extracted domain names which contain COVID or corona as substrings. Then, extracting domains which created after 2019 December 27th using freeze information, about 166,000 domain names were obtained. As for we collected website, for about 166,000 domain names which we obtained from the previous results, first we check the existence of DNS-A record and then access HTTP and HTTPS and collect screenshot and other metadata by using Google Chrome. As a result, about 75,000 screenshots were obtained. We used this 166,000 data and 75,000 data for our analysis. From here, I would like to explain how we analyze data. This figure shows the overview of the analysis procedure. First, we conducted a time series analysis of the 165,000 data by combining them with WHO data. Then, we sampled 10,000 data from the 75,000 data with screenshot and classified them by their usage. Finally, we scanned the same 10,000 data using restore tag. Now, I would like to explain each analysis procedures. First, about time series analysis. Here, we compare the daily number of COVID-19 cases and domain name registration to analyze the impact of COVID-19 on people from the perspective of domain name registration. Domain names were compared separately for GTLDs and CTLDs. For CTLDs, we considered their corresponding countries as well. The following slides show the result of GTLD and cases in the UK. The left shows the result of GTLD and the right shows the result of .uk. The blue shows the number of domain name registration and green shows COVID-19 cases. The period marked in red indicates when UK had a lockdown in place. As a result of comparison, we found that the number of domain registration reached a stable daily rate as of October 2020. We also found that domain registration increased rapidly when COVID-19 spread in April, and domain registration peaked at about a month ahead of the pandemic. From here, I would like to explain about how we investigated the usage of COVID-19 DOMs. We investigated the usage of COVID-19 DOMs based on their screenshots. Two classifications were conducted using approximately 75,000 screenshots with random sampling. First, about systematic classification. After sampling 10,000 data from 75,000 data, we systematically classify them based on whether or not they show some content. As a result, we found that about 40% showed valid content. We will now take a closer look at the 40% that show valid content. Next, I would like to talk about manual classification. To clarify the usage of COVID-19 DOMs, 3 research participants manually sorted through 1,000 websites randomly sampled from 4,188 instances of data. Categories to sort the website in were predefined and shared among the research participants. Each website were categorized by majority vote, and websites where participants could not reach an agreement were marked as unknown. Also, we developed an original GUI to speed up the classification process. This table shows the classification results. About 70% of the screenshot, which is categorized as above 5, were actually related to COVID-19, while the other 30% were not related to COVID-19 or unknown. Finally, I would like to talk about malicious domain detection. Here we scan the same 10,000 domain names used in the first stage of the usage investigation with VirusTotal, which is an online testing service to examine malicious activity with COVID-19 DOMs. In VirusTotal, scanning is done with about 70 antivirus engines. To increase the accuracy, we narrowed down detection to cases where 2 or more engines detected a domain as malicious. As a result, there were 357 detections, which mean approximately 3.5% of the sample data, suggesting that there are approximately 5,000 malicious domains in the entire dataset. We aggregated the detected categories for 357 cases by majority vote. Most were classified as phishing sites, but we can see that there are also a certain number of malicious and malware sites. So finally, conclude my presentation. In this research, we analyzed about 165,000 COVID-19 DOMs and clarified 3 findings as I mentioned at the beginning of this presentation. Since COVID-19 DOMs is registered by various people to benefit society, it is difficult to classify useful or malicious with the conventional brand ownership-based approach. Also, about a half of them haven't been used yet, so cautious monitoring is required. Finally, as a message for security researchers, since it is difficult to distinguish domains in COVID-19 DOMs, it is necessary to consider a mechanism that does not interfere with benign sites that provide useful information. And as a message for everyone, since various people have registered COVID-19 DOMs to spread information, it will be good practice to refer to official websites for reliable information. That's all for my presentation. We have published the tools and data referred to this talk here. Please also feel free to contact us. Thank you for listening.
Yeah, thanks a lot for the talk. We're a little bit over time, but I think we can continue a few minutes and actually take some questions, given this have been really interesting talks so far. If you want to turn on your video, yeah, you have. Okay, cool. Now we can see you.
Can you hear me?
Yeah, we can hear you as well. Perfect. And like, if I understood correctly, I think you will graduate this month, right? So good luck with that. And thank you for joining us in the middle of the night during this phase. Let's see, we have one question in Slack. Giovanni, let's see if we can unmute you and you can ask it yourself. We give it one more try.
All right. Do you folks hear me?
We do. Perfect.
Perfect. So thanks for a presentation. I was just wondering about your data sources. You use the zonefiles.io. that has many ccTLDs which happen to be private. Just give an example. Data now is listed there, and there is a list with 1.8 million domain names, but the entire data now zone has more than 6 million domain names. So what I'm trying to say is this does not seem to be a complete list. This may be a best effort approach, and the data may suffer from partial view. And I was just wondering if you folks did take this into account in your analysis. I haven't seen the paper yet.
Okay, thank you for your question. And so the short answer, I can't consider the data source zone files coverage. So I just use the zone file IO data and extract the corona or COVID domains from them.
Okay.
So,
okay,
yes.
hear what you say. Thanks.
Thank you.
So maybe some future work. Oliver, do you want to ask your question again? Can we unmute you?
Sure. So thanks for the talk. I was wondering whether when you analyzed the malicious COVID-19 domains, whether there was any difference in terms of when the domains were registered. So did you see, were they evenly distributed over time, or did you see any peaks with regards to the malicious domains?
So thank you for your question, and so it is a very interesting question, and I haven't analyzed about the time series analysis with malicious domains, so I will do the analysis in future work. So thank you for your suggestion.
Yeah, maybe another question from my side about malicious domains. So I also read another paper about that, like general threats, phishing mails, and so on related to using COVID as a theme went up, which I think is very much expected. That when you have like such a situation, people are afraid that this is used by threats. So do you have any comparison about you know, how many malicious domains are usually registered, and like if there have been other peaks like this or other events, or how like the whole dynamics about malicious domain like work usually?
So oh. Oh, so please ask your question again.
Sure, no problems.
Sorry.
Do you have any long-term understanding about malicious domains, not related to COVID, but like how often do people register new malicious domains usually?
So I have conducting on the malicious domain related to Tokyo 2020, and usually the malicious domain is listed from yes, usually it is registered from the big before just like before the big event. So I think that COVID is the same as it. So it is registered from the widespread of the pandemic. It is in April. It is. Sorry for my not clear answer.
It's fine, we can take it offline. Let's see if there's any last question, because we're already over time. And it doesn't look like it. So big thanks to all the speakers for providing these papers, for giving these talks. Great to have you here, and enjoy the rest of the conference. Bye.
Thank you.